So we'll begin with problems for the chapter permutation and combinations, and here's the first problem right in front of us. It says, in how many ways a team of 11 players can be selected to from a list of 16 players where two particular players should always be included in the team. So we have to select 11 players from a list of 16 players, and there are two particular players which always have to be in the team no matter what. They must be star players or something. So yeah, what do we do about this?
So for the solution of this chapter, permutation and combination, we'll be dividing the problems in specific categories, like typical problem type categories. So for the solution of this question, let's see TPC1. TPC1 says, when there's a question which says there are n objects, let's say n boxes,
okay,
and we have to select r objects from this.
Right.
With a constraint that there are p particular objects, p boxes, let's say, are always included.
Okay.
Let's say p1, p2, p3.
Right.
These are always included. So basically, our problem is reduced to the part that out of the remaining n minus p boxes, we have to select r minus p boxes.
Correct.
Because p have already been chosen.
Right.
These p have already been chosen.
And since we are choosing, then the fact that those two will permutate among themselves does not matter.
No, basically in this question, we are talking about the selection part.
Yeah.
So
So it doesn't matter what happens inside those two.
Yeah.
We just have to select them.
Yeah,
and
we
we've
have to
already
select
selected. Right.
So the question is reduced to selecting r minus p objects from the remaining n minus p objects.
Right.
And as we know that the number of ways to select r objects from n objects is NCR.
Right.
Therefore, we can say that the number of ways to select r minus p objects from n minus p objects will be n minus p cr minus p.
Correct.
This is what the formula says.
Okay.
So when dealing with the question says that we have to select 11 players for the team from 16 players.
Right.
So here we can say our n is 16.
Okay.
R we have 11 as we have to select 11 players. And there are two specific players that are always selected.
Right.
So our problem is, the solution for the problem will be 16 minus 2, that is n minus p,
Right.
c 11 minus 2, that is r minus p.
Right.
That's 14c9. So 14c9.
Right.
Yes.
Okay, so which can obviously be written as 14z5, and then on we can simply go about finding its value. So here is the solution for this problem. So again, we are going back to the top. We can see that we have to find the number of ways in which so many players could be selected out of 16 players, and we had a constraint where two players always have to be a part of the team. So we thought that we saw that it was the same thing as choosing n minus r minus p players from n minus p players, because one selection has already been made and we don't need to concern ourselves with that. So we went ahead and we used the familiar concept of combinatorials, which we call NCR, and we just put different values in place of n and r, because effectively here that is what we are doing. So this was problem 1, and we'll look at the next one now.
So now we move to the next question, that is question number 2. In how many ways a team of 11 players can be selected from 16 players such that 2 players should never be included in the team? That is, we have to select 11 players from 16 players, and we have a constraint that 2 players should never be included.
So for the solution of this question, we move to TPC2. TPC2 is quite similar to TPC1, with a difference that in TPC1 we had to include specific number of people. Now we have to take care that specific number of people are never included.
Okay.
So let's take we have n objects. Out of these n objects, we have to select r objects. Okay. And we have some particular p1, p2, p3, let's say. These particular p objects are to be never included in our selection. So basically we are left with n minus p objects to select R objects. So according to the principle, we can say that the number of ways to select n R objects from n minus p objects is n minus p CR. So when talking about the question, we have n equal to 16, that is we have 16 players, and we have R equal to 11, that's we have to select 11 players, right? And now we have 2 players such that they are never to be included. So according to the formula, we can say that 16, that's n, minus p, that's 2, CR, that is 11, is our final answer, that's 14C11.
So in this question, we have seen that we have to select R objects from n objects, and we have a constraint that p objects should never be included in the selection, and the formula comes out to be n minus p CR. So now we will move to our next question. So now we move to question number 3, which says how many 3-letter words can be made using the alphabets of the word society, so that part A of the question is S is included in each word, and part B is S is not included in any word. So now we are seeing the questions similar to the previous one, but the thing is that we also have to, I think, arrange them.
So the solution of this question can be proceeded like from TPC3 and TPC4. TPC3 and TPC4 is very similar to TPC1 and TPC2, with the difference that we have to arrange the alphabets. When we come to arrangement can be done in 2 ways, in basically 2 steps. The first step is to select the selection of objects, like we were doing in TPC1 and TPC2.
Okay.
And the second part is the arrangement. So when seeing this question states that we have to make 3-letter words from the word society. So the word society, such that we have to include always S. We have to always include S. Now the leftover word is OCIETY.
Okay.
So the selection part is actually TPC1, where we had to always select a particular number of objects.
So basically this question is an extension of TPC1, such that we have to arrange them also.
So now the leftover part is we have to select two letters from the rest 6. So the number of ways to select 2 letters from the rest of the 6 are 6C2. Now that we have 3 letters, S plus the 2 selected from 6C2 selections, we have to arrange them, and the number of ways to arrange 3 objects is 3 factorial. So we can say that the total number of ways to arrange to form words, 3-letter words from the word society is 6C2 into 3 factorial.
Okay. Now we move to the next part of the question, that is S is never included in the selection.
When talking about the next part, the B part says that you have to always exclude the S alphabet. So this is also an extension of TPC2. TPC2 states that some number a specific P particular objects have always to be excluded. So we have to select the remaining 3 from these 6 letters.
So second part is extension of TPC2.
Yeah. The number of ways to select 3 letters from 6 letters is 6C3. And now as we have 3 letters, we have to arrange them. So we multiply by 3 factorial. This is the number of ways to arrange the 3 letters so as to form words in which S is always included in A part and S is always excluded in the B part.
So in this question, basically we see that these 2 questions are extension of TPC1 and TPC2 that we have seen earlier. The thing is that we have to arrange them also. First we have to select them and then we have to arrange them also. And to do this question, we can also apply the formula. The logic is already explained to you. We can also use the formula, that is n minus p c r minus p into r factorial for the first part, and the formula n minus p c r into r factorial for the second part. So now we'll move to our next question. Thank you. now we move to question number 4, which says arrange the letters of the word university such that all the vowels are together. And the second part of the question is we have to arrange the letters of the word university such that vowels and eyes are together. So basically now we move to arrangement of objects in which we have to keep p particular objects always together. So let's move to the solution.
For the solution of this question, we consider TPC5. TPC5 says that when there are TPC5 is basically for the questions in which some p particular objects are always together in the arrangement. So let's say we have n objects and p of them, p objects are always together.
Okay.
So let's say we have n boxes. And out of these n boxes, these p boxes are always together. So we consider them as a group.
Whether these p boxes will be together, any p boxes can be together.
There are particular objects are always together. So in the question they'll mention which p objects are to be selected.
Okay.
So we consider them as a single group. Now the number of objects we are left to arrange are n minus p plus 1 this group. This group is taken as one object.
Okay.
So now we arrange these n minus p plus 1 objects in n minus p plus 1 factorial ways. Now we have arranged the upper layer. We have to consider the arrangement of this group also. The p objects inside the group are also different, so we have to consider the arrangement of these p objects also. So for the arrangement, for the total number of ways, we have to multiply n minus p plus 1 factorial by p factorial, where this p factorial is basically the internal arrangement of this object, which can differ according to the p objects.
So basically what we are doing is we are considering the p objects as a single object and we are arranging them, and then we move inside the box, that is we have to arrange the p objects also. So now we'll move up to the question.
The question, considering the question, we say the question, in the question we have to arrange the words, the letters of the word university. University has, the word university has 10 alphabets. So let's write them like this: UIIE, and rest of the consonants are written separately. So now as the vowels have to be kept together, we consider this as a group, all the vowels as a group, and the rest 6 as different objects. So now we have total 7 objects, 6 consonants plus 1 group to arrange. So there are 7 factorial ways to arrange them.
Okay.
Now we have considered the selection, we have considered the arrangement of these 7 groups. We move to the arrangement inside the group. The arrangement, for the arrangement inside the group, we have 4 objects, but we have to take care that out of these 4 objects, 2 of them are similar, 2 of them are alike. We have 2 eyes. So the number of ways to arrange these 4 objects will be 4 factorial upon 2 factorial. This 2 factorial is to make sure that the arrangements are not repeated, because these 2 are alike. So the number of ways to arrange them will be 7 factorial into 4 factorial by 2 factorial. Now we move to the B part of the question. The B part of the question says that the vowels as well as eyes are also together. Now, in the first part we have seen that the vowels were together. Now it is an extension of the first part only. Now we have to consider in such a way that these eyes are also together. So first of all, we make a group of vowels and the consonants, like in the first part. Here also we have total 7 objects, and these can be arranged in 7 factorial ways. Now we have to consider the arrangement inside the group, but now inside the group we have 2 objects, U, E, and 1 group. So there are total 3 objects to be arranged in 3 factorial ways. and when we move again inside the group 2, the group of i's, we have to arrange them. But the arrangement of two i's can be done only one way, because they are alike. So the arrangement will be 2 factorial upon 2 factorial, that is 1. So they can be arranged only in one way. So this will be the total number of ways we can arrange the objects such that the vowels as well as i's are together. So in the first part we have seen that the vowels are together, and in the second part we have seen all the i's are also together.
So we learned the technique how to do a problem in which we have to arrange the objects such that p particular objects are always together. So from this question we see that in the first part we kept all the vowels together. So basically what we have to do is we have to treat it as a single object, the items which are to be kept together, and then we have to go inside the group and consider their arrangement also. And second part is basically extension of first part, that is in this i's are also to be kept together. So we have to just multiply the one more term, that is 1 in this case. So now we move to our next question. So now we move to question number 5, that is 9 candidates are appearing for an exam, 3 are appearing in mathematics, 6 in others. So in how many ways can they sit such that all the mathematics students are separated? So now we move to next class of problems, which says that some particular object should always be separated in the selection.
For the solution of this question, let's see TPC 6. TPC 6 says that we in some p particular objects are always separated in the arrangement of n objects. So let's say we have n objects. These n objects, let these n objects be C1, C2, C3 and R1, R2, R3. These are n objects,
Okay.
of which these C are always to be kept separate. When we say that they have to be kept separate, that means that no two of them are to be together. No two of them is together.
So that's the meaning of separation.
Now let's consider these objects. Let's consider the remaining n minus p objects and arrange them. Arrange these n minus p objects. The number of ways to arrange these n minus p objects is n minus p factorial.
Right.
And after arranging these, we see that we are left with n minus p plus 1 remaining spaces for the rest p. So now for these p objects, the remaining p objects, we have to select places from the rest n minus p plus 1 places. So the number of ways to select p places from n minus p plus 1 places is n minus p plus 1 cp. Now we have chosen p places from these n minus p plus 1 places. We have to arrange the rest p objects. The rest of the p objects we have kept there. So we can arrange these p objects in p factorial ways. So the total number of ways in which we can arrange these objects so that these particular p objects are always separated is n minus p plus 1 cp into p factorial into n minus p factorial. So now when we consider this question states that we have 9 candidates appearing for the exam, of which 3 are mathematics and the rest 6 are of other subjects. We have to make an arrangement so that these three students are always separated. So first we make the arrangement of these 6 students. These 6 students can be made to sit in 6 factorial ways. Now we have remaining 7 places, of which these 7 places we have to choose 3 places so that mathematics students can be placed. We can choose 3 places in 7C3 ways, and then we have to arrange these 3 students in 3 factorial ways. So the total number is 7C3 factorial into 3 factorial into 6 factorial. And if we use directly the formula, we can see that n was 9 here and p was 3. So according to the formula, the answer would be 9 minus 3 plus 1 C3, that's p is 3 and n is 9, into 3 factorial, where it is p factorial, into 9 minus 3 factorial, that is 6 factorial. So we see that it is same as the answer we got logically. So this problem can be approached in two ways, by formula directly or by this logical approach. Although I would suggest that it is better to approach logically so that you don't make errors in the question.
So now we see that we have done the problem in which we have to arrange the objects such that p particular objects are always separated. So basically the thing is, we have to first arrange the n minus p objects in n minus p factorial ways, and out of n minus p plus 1 spaces, we select p spaces for p particular objects which are to be always separated, and now we have to arrange them. So the total number of ways becomes n minus p plus 1 cp into n minus p factorial into p factorial. So now we'll move to our next question.
So moving on to problem 6, we have teams of 5 are to be selected from 4 girls and 8 boys such that at least 2 girls are included. So again, we have 4 girls, 8 boys, and we have to make a team of 5 out of them. And in each case, in each of these teams, there should always be at least 2 girls.
So for this question, we consider TPC 7. What TPC 7 says is, whenever you have an at least or at most constraint in the question, you have to always make cases. Otherwise, you end up getting wrong answer.
Right, and you'll have to make cases because, you know, in when you are dealing with permutations and combinations, at least at this level, you have to deal with equalities. You know, this, what if this is equal to this, and you have to do this and this. If you have an inequality there, for example, at least or at most, then you have to consider all of those individual cases which satisfy that inequality, and that is why you make cases here.
So now we make cases. We start making cases. We have we have to make a team of 5 people, and we have 4 girls and 8 boys.
Right.
So the cases can be, we can have 4 girls and 1 boy. We can have 3 girls and 2 boys.
Right.
We can have 2 girls and 3 boys. Or we can have 1 girl and 4 boys.
Right.
No, we cannot, because there is a constraint that you cannot have less than 2 girls. You have to have at least 2 girls. So this case is not to be included. So let's consider the first case. The first case says that you have to select 4 girls.
Right.
So we make the selections now.
Okay.
This selection, how do we make selections? The number of ways to select 4 girls from 4 girls is 4C4.
Right.
And the number of ways to select 1 boy from 8 boys is 8C1.
Right.
And here we are multiplying the 2 because both the selection of girls and the selection of boys is independent.
Okay.
And according to the multiplication principle, we can say that these two multiply, when we multiply these two,
right,
we get the total number of ways.
Correct.
So now considering the second case,
right,
the second case says you have to select 3 girls out of 4. So these can be selected in 4C3 ways.
Right.
And
you can see that we have to just, you know, go on making tables of each selection, and we can arrive at that the conditions that will be for each case, and we just have to write how the number of ways in which we can make it, we can make the selection for those particular cases. And since it says at least, so all of these possibilities are correct, so we'll add them, or
yeah, we'll add them.
Okay, because all of these conditions will satisfy, and that is why we use the principle of addition here. No, yeah, but then after we have got the thing.
Now so now we see another way to do this question. In the first part, we proceeded by making cases from the forward way. Now we go backward. What do I mean by backward is, let's first select all the 5 people from the total number. That's
okay,
12. Okay, and then we subtract the cases which we have to avoid, And what the cases which we have to avoid are, let's say the cases are, we have one girl and 4 boys, because the constraint was you have to have at least 2 girls. So this case has to be subtracted. The second case is when you have 0 girls and 5 boys. So these two cases have to be subtracted, because you have a constraint that at least 2 girls are needed. So the number of ways for the selection of this case is like, we have to select 1 girl from 4 girls, so 4C1, and 4 boys from 8 boys, that's 8C4.
So basically, now what we are doing, we are just subtracting the cases which we do not need. That is, we do not need that in the selection there should be less than 2 girls. So we are subtracting the case in which there is 1 girl and there are no girls from total number of cases.
So the final answer will be 12C5 minus 4C1 into 8C4 minus 4C0 into 8C5. That's the final answer. And
Okay.
we see that when we sum up the first case and we find the second the answer from the second case, they both are same. The only difference is here we proceed backwards. In the second method, we proceed backwards.
So basically in this question we have seen that there are 2 methods to do this question. The first one is you proceed by making the total number of cases that we need, and the second case is from the total number of cases that is possible you subtract the number of cases which are not required. So now we'll move to the next question.